Welcome back, ladies and gentlemen. We're going to be looking at significant figures today, and why do we need to worry about this? Well, specifically in science, when we work with numerics, typically there's a measurement that has been done or performed, and when we make that measurement, we are actually estimating the last digit that we report on that measurement, right? As an example, I'm going to switch. Let me see if I can add a page here. All right, so let's say that we have some fancy schmancy ruler. We'll go ahead and put this little fancy schmancy ruler in like so. And this ruler will have markings. All right, so we'll do like 1, 2, 3, 4, 5. And then 1, 2, 3, 4, and a 5. And then 1, 2, 3, 4, and 5. And 1, 2, 3, 5, and so on. All right, let's say that this every mark we'll say is like a halfway point. So this is like, this is 1 and this is 2, and let's just say that these are centimeters. All right, so centimeters here, centimeters here, and so this obviously at the bottom would be 0 centimeters. Okay. So, say we're going to measure some object. So we'll sketch a rough, crude object, like some sort of metallic rod. So we'll just put like a little bent piece of wire or something that we're going to measure. And what we want to do is, again, measure with the highest precision possible. All right. And so we would look at this length of wire, and we'd say, all right, well, we know with absolute certainty it's greater than 1 centimeter, but less than 2 centimeters because the end of this falls in between those two markings. We know that this is 1 centimeter for sure. We know this is 2 centimeters for sure, but it's not 2. It's less than 2, but more than 1. So for our measurement, we write down, all right, well, it's 1 centimeter. Well, we know that there's portions or a partial centimeter as well. So we'd say it's 1 point something. Okay, so let's go ahead and we'll grab a line tool. All right, and we will draw a dotted line here as straight as we can, like so. Okay, so looking at where this falls on the scale, we know that it's definitely more than 1.1, 1.2, 1.3, 1.4, 1.5, as well as mark that in as 1.5 right here. Right, and so we know for sure, because of these markings, it's more than 1.6, it's more than 1.7, but it's not more than 1.8. All right, so it's somewhere between those. But I know for sure that this next digit has to be 1.7. And now this is where we make that last digit of estimation. We would not be done measuring the cylinder or this length of wire. We would actually have to provide 1 digit of estimation. So I'm going to underline this position right here. Right? You do not need to underline this, but I'm just going to show you that this is the position that we are estimating. Right? So we're going to look between these two markings, and if we think it's halfway between these two, then we'd say, well, it's 50%. That'd be 5 units between these two. If we think it's a little bit less than halfway, and again, I drew this by hand, we'd say like maybe 4 or 3. But one thing that we could look at this and know for sure is we can all agree that it's not very close to either one of these lines. So, this should not be a 0. This could not be like a 9. We know it's somewhere between these two. And so I'm going to say that it's probably like 40% of the way there. We express measurements with certain values that we know for sure and a value that's estimated. All right, so this obviously would be our estimated value. And this is true for any time we use any type of measurement scale or even a digital scale. The very last digit that it's giving you is a rounded estimation of the digit it would not display on the screen. All right, so this is kind of why, I guess, the purpose behind significant figures. Because say we want to find like the volume of the cylinder, we're going to use this measured value for one of our mathematical operations, right? This will be the height of the cylinder. We would then multiply by the area of the surface of this top of the cylinder as well to get the volume. And so some of this estimation will get carried in inevitably into our calculation for volume. And so noting and keeping track of how many digits are significant, meaning numbers that we actually know with certainty, and the numbers of digits that we estimate will help keep our final measurement that we report for a calculated value within a reasonable number of digits. Okay, so that's a really quick crash course on why we use sig figs. All right, so let's hop into actually like how do we evaluate, whoops, let's go back here. How do we evaluate the number of significant digits? All right, so I'm going to show you a few tricks to evaluate the number of significant figures when provided a number. So let's say we want to know, we'll work with number one, okay? We want to know how many digits are significant to provide this measured value. Now, let's consider this number, this 5.432. What's interesting about this number is all of these numbers are all non-zeros, right? So that means that there had to be some scale where we knew the 5 for sure, the 0.4, the 3, and this must be our final estimated digit that falls somewhere between, a little bit beyond the hundredths, 300ths, but a little bit less than 400ths, obviously less than 400ths. Right, so when we try to determine the number sig figs, what I like to use is the box and dot method. Right, so here's how it works. You make a box between the leftmost non-zero digit and surround then the rightmost non-zero digit, and anything that falls inside that box is significant, right? So this number here would have 4 significant figures because they're all non-zeros. All right, fair enough, simple enough. All right, let's apply this to number 2. All right, so again, we're going to use our box and dot method. So we're going to start our box on the leftmost non-zero digit. We're going to surround all the way to the rightmost non-zero digit, and that gets enclosed inside our box. And everything found inside that box is significant, right? So we would have, in this case, 5 sig figs for this number. So we know all these with certainty, and that final digit is the estimated one. All right, we can also apply this to number 3, very easy, leftmost to rightmost, and we would say that there are 3 significant figures or sig figs in this number. All right, 4 is very easy. Again, we just surround them all with a box, and there'd be 4 sig figs. All right, so now in number 5, we have an interesting situation because now we have a leading 0. And leading zeros are never significant, but if you don't remember the rules for sig figs, this is an easy way. Just use the box and dot method, right? So we start with the leftmost non-zero digit, which is the 0.1, all the way to the rightmost, and so this number has 3 sig figs in it. All right, let's hop across the column here because I'll let you kind of work through the rest of these on the left-hand side. On the right-hand side, there's a few situations that might be interesting for us to evaluate. All right, so in number 11, again, we use the box and dot method. So we're going to box around the leftmost and then the rightmost non-zero, which is the 2 and the 5. And so this number actually only has 2 sig figs in it. Now you might ask yourself, well, why is it only 2 sig figs? It's 2,500. There's 4 digits there. Why only 2 sig figs? Well, consider the values that were being given in this measurement. We know the 2 with certainty. We know the 5 probably maybe from certainty, but this could be our estimated digit, or even it's possible that it's right on the line or something, and so we would put a 0 down. But then this extra 0 is just simply a placeholder. It's not necessarily found on the measuring device, and so therefore, with significance, we only know it to these 2 digits. Now, if we look at number 12, the situation is different. Now, we call it the box and dot method because we also pay attention to whether a decimal point is present or not, and that's where the dot comes in. All right, so we're going to start our box on the leftmost non-zero digit, the 2, and we're going to continue, but we're going to stop for a second right here. Now, our rightmost non-zero digit is the 5, but we also have an included decimal. So what are they trying to tell us with this measurement? What they're telling us, or what you would be telling me, is that you know somehow this measuring device has hard lines all the way to the ones position, and this is your final digit of estimation, which means that this is a significant value. Like you know that it's zero point 0. It must be like on the line or something. So we would actually continue our box to include the dot and anything that follows after the dot. Right? So even if it's a 0, if we put a decimal in a number and we should express the zeros after that decimal point, we are telling you that we know that measurement all the way to that position. So this one actually, because the decimal is included, would have 5 significant figures. All right. In number 13, we do not worry about powers of 10, okay? So don't even look at those when you look at significance. We are going to worry about the coefficient here, though, right? So this 1.04, we're going to use, again, the box and dot method. And so if we have a decimal here, everything to the right of that is significant. And so this would have 3 sig figs. Now, actually, a trick here is if you want to help, I guess, reduce a number to simply the numbers that are significant, you can convert the number to scientific notation. All right, so if we want to convert this into scientific notation, all right, we simply need to follow some very simple rules. We move the decimal. This one has an implied decimal. We'll move that to where there's only one digit to the left of the number, and then we need to multiply by power of 10 to show how many powers of 10 did we pull out of the number, or how many powers of 10 did we give the number to bring it into the standard form for scientific notation. All right, so this becomes 2.5. Now, why don't I include these zeros over here? Well, because I didn't have a decimal point. Because this decimal point has not been given, I do not know these numbers with certainty, and so therefore I'm not required or obligated to carry them into my coefficient. Right? So you can see right away where the coefficient now has been reduced to just the 2 digits that were significant. And then we could say it's times 10 raised to the third, because we pulled 3 powers of 10 out of this big number. These are powers of 10 that I already had, so we could say that these are positive exponent here for the powers of 10. If this was a very small number, like point something, then we'd have to give it powers of 10 to bring it into this form, and we'd owe those back, and so that would result in a negative exponent. To get back to the original number, we would multiply by 10 3 times. All right. Another way we can write this scientific notation, and you may come across this in your book, but we'll definitely want to use it as we write things down because it makes things a lot easier to write. We could write down 2.5 like normal, and then we can replace this times 10 raised to something. Like we can replace that with a big capital E, right? So 2.5 big E to the whatever the exponent or raised to power is. In this case, it's 3. So 2.5 big E to the 3 is the same thing as 2.5 times 10 raised to the third, which is the same thing as 2,500. Okay, so what about the, oh yeah, before we move on, as we can see, moving this into scientific notation gives us just the 2 sig figs. All right, so what about the other one? Does it work with this trick as well? Sure does, right? So if we do, let's see, 2,500.0, all right, that was the original number from the previous problem. All right, to move this into scientific notation, now because this decimal is here, by the rules of scientific notation, I am obligated to keep all of this stuff in my coefficient. So when I convert this, it'll become 2.5, and I got to keep the 0, and the last 0. And then that's going to be times 10 to the third, as we had done before. We can also rewrite this as 2.5000 times 10, this big E raised to the third, right? Notice that this then shows us that this number has 5 sig figs, because that's what the coefficient is. So a number in proper scientific notation, the coefficient will have the number of digits that are equal to the number which are significant. Okay, let's hop back. All right, so we can, I mean, the rest of these I think kind of help, you can kind of use these rules to help you. Let's do number 17 real quick to finish up. Again, we're going to start our box to the left of the first non-zero digit, but notice that we have a dot present, right? A decimal position is given to us. So that means that anything after the first non-zero digits are significant, right? So we would put a box around the 2, the 3, and the 0 and the 0. So there are 4 sig figs. All right, now on to the enlightening portion. How do we then apply these significant digits to mathematics? Right, well, there's 2 rules that we really need to know. The first one applies to addition and subtraction. The other one applies to multiplication and division. Now, one thing to consider is like, when do I apply the rule? Do I apply the rule when I've done every single math operation completely, or what? What you're supposed to do is actually apply the rule when you're done with that type of operation. So if you're adding or subtracting, when you're done doing that addition or subtraction with those numbers, then you apply the rule of significance before you go on to switching into multiplication and division, or vice versa. But for most people, I've found, most instructors, I've found that they, as long as you apply significance to the problem overall, they don't get too tied up as to like, when do you actually apply it? Like, do you apply it several times throughout the problem? Usually they say wait to the very end and then apply the rule that would be, I guess, most important to keep forward. Usually the multiplication and subtraction, or multiplication and division, is the one that we need to follow. All right, so you'll see why. All right, so let's consider this problem we have here. This is number 1 on the addition section. So we're adding these numbers up. All right, so 12 centimeters plus 0.031 plus 7.969. Now, what's interesting about addition and subtraction is the rule is your answer cannot have any more precision. It can't be more accurate. Well, we don't want to say accurate. Your answer cannot be any more precise than your least precise measurement, which makes sense. I mean, obviously, when they were measuring this, like, they used a very precise ruler measuring device, and they wrote numbers down, were very careful in measuring this third term also. But this first term is just 12 centimeters, so Lord knows what happened here. Maybe, Joe, the terrible lab partner, really didn't pay much attention, just said, it looks like 12, so wrote down 12. All right, so what that's going to do, though, that's really going to cut us down in terms of what can we hang on to into our final answer. All right, so let's add these numbers up. I'm going to switch over to my calculator here. And so we take 12, we're going to add 0.062, sorry. All right, so let's switch to my calculator here. We're going to take 12 plus 0.031 plus 7.969. All right, and it comes out to a nice even Steven 20. All right, so when we go to write this down, then we have to consider, like, to what precision are we allowed to express this answer? Well, we kind of lucked out here because these all add up to 20, and we're actually allowed to express down to the ones position, because in addition and subtraction, you're restricted by that which is the least precise. And that's this 12, this whole number 12. So we're not actually permitted to have anything after the decimal point. We can't even show the decimal points. It's got to be 20. All right, so that's how we handle addition and subtraction. Let's do one more just to kind of hit it home here with what we are doing. All right, so let's consider number 2. All right, so we're going to add the series of numbers up. All right, so we'll take our 0.085. We're going to add to that 0.062 plus 0.14, and this comes out to 0.287. All right, so we're going to write that number down, 0.287, 0.287. All right, now we have a problem with this answer. We can't leave it like this because we are actually restricted to the measurement that has the least precision, and that is going to be this one right here, this 0.14. It only allows us to report answers to the hundredths position, which means that we have to stop our number here. So we'll have to use rounding rules to finish this out. This will be then changed to 0.29. All right, so this will be changed to 0.29 centimeters. And I should probably put the units on this. I'll be in trouble if I don't. There we go. So again, the reason for that is addition and subtraction. You always go after the one that has the least precision or the fewest decimal positions is what most students kind of just remember. All right, so in number 3, you could go to the third decimal position in your number. In number 4, looks like you can go to the 10th spot, and that's it. And so you really kind of apply that rule all the way through, whether it's addition or subtraction, doesn't matter. Okay, so let's take a look at then multiplication and division. How do we handle those? All right, now with multiplication division, your answer is, the rule is that your answer is restricted to the same number of significant digits as the one with the least, or the one with the fewest, from the numbers that you work with. All right, so we're going to hop down here. We're going to choose, let's choose number 4. All right, so we'll use number 4 here. All right, so we're going to go ahead and do the math here. So we take our 5.00, and we're going to multiply this by 7.3216, and we'll hit enter. All right, and we get 36.608, so we'll write that down. 36.608. That's millimeters, but we're not done with it yet. All right, so here's the rule. When we multiply or divide, our answer can be no more significant than that with the fewest. So our first number here has 3 sig figs. Our second term or number here has 5 sig figs. So our answer can will have to be restricted to the first 3 significant digits. So that means the 3 will, let me change colors for a second. That means that the 3, the 6, and then this final 6, that's our third sig fig. So that's where we have to stop. We would apply rounding rules. It's followed by a 0, so we don't round it up. We leave it as it is. And so our final answer, and we'll go ahead and grab an eraser here. Our final answer would be 36.6. All right, and then also remember that whatever we do to the numbers, we also do to the units. So this will actually be millimeters squared because we're multiplying one dimension by another. All right, and let's hop to number 6. All right, number 6, we're taking 5 centimeters multiplied by 5 centimeters. We know that the answer is going to be, without using a calculator, 25. That'll be centimeters squared. But we have a problem. Each of these numbers only has 1 sig fig. So this number can only also have 1 sig fig. So, well, if we look right down the 2, we see right after it, it's followed by a 5. We're just going to round it up. And you're absolutely right. Even though this feels absolutely wrong, we have to follow the rules of significance here. And our answer would actually be 30 with no decimal point because we do not want this 0 to be significant, and that'd be centimeters squared. So this would be our final answer for number 6. All right, like in number 7 here, we have 5.0 times 5. We're still going to get, 25.0 centimeters squared for an answer. However, we're restricted by the number with the fewest sig figs. So we can only have 1 in our answer. So that's going to round the 2 up to a 3. This will also be 30 centimeters squared. All right, now number 8, thank goodness they allow us to have 2 sig figs in our final answer because we have 2 sig figs here multiplied by 2 sig figs here. So 5.0 times 5.0, that gives us 25 and centimeters squared. We're allowed 2 sig figs, the 2 and the 5. So when we start to write these numbers down, we always work from the highest placeholder to the smallest. And every non-zero you write down is going to be significant. In the case of 30 here, we know that there's not a decimal point here, so our box and dot method would say that just the 3 is significant. So sig figs can be a little bit daunting at first, but the more you work with it, the less that is. So give these a shot, and I'll be posting the key to this in the very, very near future.